All right, my lovelies. Welcome, everybody. It is time for us to begin. In front of you, you should have your periodic table. You should have a single colored pencil, and you should be coloring in the alkaline earth metals. This is everything in column 2A. Everything in column 2A you want to be coloring in. Now that you all have had time to color in our alkaline earth metals, which is group 2A, things we're going to talk about today. We're going to talk about the alkaline earth metals. Basically, everything you need to know about these elements is right there in the name. They're alkaline, they're from the earth, and they're metals. So we'll talk about all of the ways in which these things are important. You're going to shade in, if you haven't already, column 2A. We will also fill in the charge of the ions these things make above it. We're going to talk briefly, we're going to review how parentheses work in a chemical formula. That is going to be a skill that's going to start showing up on class kicks now, the usage of parentheses. And we will spend a little bit of time talking about conflict minerals. Right, so when we are mining things out of the earth, where is that coming from? And what are the consequences of purchasing some of those things for the people involved? Okay?
Anna,
yes. So you're going to want a key. So you should have the alkaline earth metals with like a square that's colored in whatever color you colored them, labeled alkaline earth metals, and it should be under the metals section. Alright, so you should have this group colored in. You should have a key where these are listed alongside the alkali metals in the metals section, so you know that those things are also metals. Yes?
Can you just write metals after them and know that they're metals?
I mean, it is your periodic table, so whatever works for you is fine. The main thing I want to say is it is important that you be able to tell the difference between metals and non-metals on the periodic table. Alright. These here are the alkaline earth metals, and you can see them laid out from beryllium to magnesium, calcium, strontium, barium. Radium is not pictured because that's a little bit more expensive, but the rest of these are laid out here. I also have a little bit of magnesium up here. Later on in this unit, when we get to chemical reactions, I'll show you a fun chemical reaction that we can do with some magnesium metal. But these things are fairly common. Magnesium is also the metal that my laptop here is made out of, right? So like MacBooks tend to have magnesium in them. When you look at these, for the most part, these look like regular metals, right? Gray rocks. Anyway, back to these alkaline earth metals. A thing I want to point out, 2 of these alkaline earth metals have been stored here in oil. The others are just left out. Here is a little bit of a puzzle I want to have for you. Based on what you know about the alkaline metals, why do you think it's those 2 metals, strontium and barium, that were stored under oil as compared to beryllium, magnesium, or calcium? Why those 2? Why do those ones need to be stored specially to keep them safe?
You don't feel like they're really reactive?
They're really reactive. How do you know that those 2 are the ones that are going to be really reactive? Lisa?
Because they're lower down in the table, and for metals, because metals react by losing the electron. It's easier to lose the electron the bigger the atom is because it's further away from the center, so it's easier to lose it, so it's more reactive.
Exactly correct, right? As we go down the periodic table on the metal side, we are more reactive, right? So these are the ones that react really easily, so they're harder to store safely. So here they are stored in oil, so that they don't react with oxygen from the atmosphere. So, just a fun way to apply that bit of knowledge already. Let's get started with having you practice drawing some atoms. So planetary models. I want to see planetary models for beryllium, for magnesium, and for calcium. As you're doing this, as always, I want you to pay attention. Like, hey, if these things were to form an ion, how would they do that? What would the charge of that ion be? So let's draw some planetary models.
Looking anyway.
All right, I'm hearing the volume increase, and that suggests to me that folks are finishing up. So let's look at some of these. So first off, beryllium. 4 protons, 5 neutrons. Make sure that you wrote down 5 neutrons.
Right.
because the number of neutrons is not just the same as the number of protons. You have to take the mass number, round it, and subtract the number of protons. And then we've got 4 electrons, 2 of which can go in the inner shell. Then we've filled the inner shell, and then we can place the next 2 in the next shell out. For magnesium, 12 protons, 12 neutrons, because its mass is 24. We've got a total of 12 electrons, so 2 in the first shell, 8 in the second shell, 2 in the third shell. One thing I want to point out, I am not going to be picky about how you do the inner shell electrons. Like if you see here, the beryllium one has an electron north and an electron south. I think that's how I taught you. That's totally fine. It is also acceptable to do it how we did in magnesium, where there's just like a single pair in the first shell. I'm okay with either of those approaches. So I'm not going to be picky about that. There's different teachers who teach it different ways. And then lastly, calcium. Calcium's in the 4th row of the periodic table. So we have 4 electron shells that we have to draw. The outermost one has 2 valence electrons because it's in column 2A, and all the inner ones are full. So, looking at this, the key characteristic is what?
They all have 2 valence electrons.
We've all got 2 valence electrons. So some things I want to point out about 2 valence electrons. If these things want to form an ion, how are they going to go about fulfilling the octet rule? Talia?
By losing the outermost electrons.
Yeah, they're going to want to lose those 2 outermost electrons. And if we lose 2 negatives, if we subtract -2, if we take 2 of the cold cubes out of the soup, what does our charge become? +2. So all of these ions are going to have a charge of +2. Something else I want to point out about this. Is there any way for these guys to become stable, to fill their outermost electron shell with covalent bonds?
No.
No. This cannot become stable using covalent bonds. Because even if they share each of those pairs, they'd only end up with how many electrons, Missy?
4,
They'd
not
only
8.
end up with 4. They need 8 to be stable. So can these things do covalent bonds?
No.
No, they can't do covalent bonds. Typically speaking, we only see covalent bonds among non-metals, right? Whereas the metals, like the alkaline earth metals, can either do ionic bonds, where for these guys they'd have a charge of +2, or they can do metallic bonds where they just share valence electrons willy-nilly. All right, so these things are going to have 2 valence electrons. When they form ions, their charge is +2. So above column 2A on the periodic table, please be sure to write a +2. So +2 on your periodic table above their column, just so you have down the charge of their ions.
Wait, should we write a -1 above halogens?
Yes, there should be a -1 above the halogens, and a +1 above the alkaline earth metal, or above the alkaline metals, and a +2 above the alkaline earth metals. All right, so we're going to go through. Most of what you need to know about this group is right there in the name. So first off, the alkaline earth metals, they're metals. So they have all the metal properties. You shouldn't need to write these down in your notes because you already have these down in your notes. They're malleable. We can hammer them out into sheets. They are ductile. You can draw them out into wires. They're conductive. They easily transfer electrons from one atom to the next. And they always form cations, which are positive. Oh, that was a weak perception. Y'all must be tired. Can you pretend that you're full of energy and still find my puns amusing? They form cations, which are positive. Thank you for pretending you have energy today. I appreciate it. All right. So that is all stuff that by now should be pretty familiar to you. We've talked about several groups of metals. The second part of the name, the alkaline earth metals, they are alkaline. Now, we talked about what the word alkali means when we talked about the alkaline metals, group 1A. Who remembers what alkali means? Emily? Yeah, it means they form bases. So the alkaline metals form bases. The alkaline earth metals also form bases. They just aren't quite as good at it. While the alkaline metals, group 1A, form strong bases. The alkaline earth metals form weak bases. Now, the difference here when we say strong versus weak, what that actually refers to is, so these are ionic compounds. when you stick an ionic compound in water, it can dissolve. Just like if you stick some salt in some water, it can kind of dissolve, right? The salt's just kind of everywhere mixed in between the things. You can't see the individual grains anymore. When you stick a strong base in water, it dissolves fully so that every single, alkaline metal cation separates from every single hydroxide anion. So every time you put in a molecule of a strong base, you're going to be adding a single unit of this polyatomic anion that makes things a base, the hydroxide anion. That's what a strong base is. Same deal for a strong acid, by the way. When you put a strong acid in a solution, all of the hydrogen cations pop up off of the halogen anions. A weak base or a weak acid just means they don't all separate. Yeah?
Does that mean they go with the one, oxygen?
They are going to be able to bond with hydroxides, and we'll talk about what that means.
No, because lithium, the halogens and the alkali bond with together.
Mm-hmm.
So is there one that the alkaline metals?
These absolutely can bond with oxygen, right? When they bond with oxygen, they would rust. Yeah. So things in column 6A, but they're not quite as perfectly paired. Like the alkaline metals and the halogens really are like this sort of perfect set of counterweights to each other, whereas that's not quite as obvious or as beautiful with column 6A and column 2A. All right, so they're alkaline. They can make bases, but when they make bases, they make weak bases. So if we're keeping track of our types of chemical over here, we can add another one to the list. An alkaline, actually let me scoot this over so you can see it. So here's our different kinds of chemical compounds that we've learned about. And we learned that the alkaline metals with a hydroxide anion makes a strong base. Well, the alkaline earth metals can bond with two hydroxide anions and make a weak base. So there is a very good similarity here, but the key difference is it takes a pair of hydroxides to balance out those two positive charges from the alkaline earth metal. Because hydroxide, right, this polyatomic anion, it has a charge of -1, so it only has a single negative charge. But we just said, hey, the alkaline earth metals, they have a charge of +2. So if we have two positives from our cation, from the alkaline earth metal, we're going to need a total of 2 negatives. And if each of the anions we're using only has a single negative charge, we'll need a pair of them. So let's talk about how we represent that. To do that, we need to use parentheses. So, let's say we have an alkaline earth metal like beryllium. We just said when beryllium forms cations, it forms cations with a charge of +2. Now what we want is to make a weak base with this. So to make this a weak base, the beryllium is going to be paired with hydroxide anions. Remember, hydroxide is that polyatomic anion that's a piece of a water molecule, an oxygen and a hydrogen really tightly bonded together, and collectively they have a charge of -1. I can't just have a single hydroxide, because then I only have 1 negative charge and 2 positive charges. I want to have a pair of these. But I can't just stick a 2 down here, because if I stuck a 2 here, it would only reference the hydrogen. When what I want to reference is the hydroxide, this whole thing. So in order to show this, I just used parentheses. I take that OH minus, I stick that whole thing inside parentheses, and I stick a 2 outside of the parentheses, like this, to show that there are 2 atoms, or 2 ions of hydroxide in this chemical compound. So now in total, we have 2 positive charges from the beryllium, and then we have 2 hydroxides, each of which has a charge of -1. So in total, I have 2 positives and 2 negatives. Now this brings me to something really interesting, because the name of this chemical compound is beryllium hydroxide.
does that make?
This is a weak base. So this chemical right here is a weak base.
No, but like, is it a chemical that we know, like baking soda?
No. Baking soda is sodium bicarbonate, which it's a different, bigger molecule. So beryllium hydroxide is the name for this. I don't think there's really a common name for it. But with ionic compounds, the way we name them is pretty simple. It's just the name of the cation followed by the name of the anion. So our cation is called beryllium, our anion is called hydroxide. So this is just called beryllium hydroxide. Something I want to point out about this name. Nowhere in the name does it tell you that there's 2 hydroxide ions. With the names of ionic compounds, it doesn't tell you how many of each ion there are, because you don't need to be told since you have the tools to figure it out yourself. The general assumption in chemistry is that if you hear that something is called beryllium hydroxide, you sitting there can go, oh, I know that beryllium has a charge of +2, and I know that hydroxide has a charge of -1, and I know that an ionic compound as a whole is neutral and has no charge. That means that I must have to have 2 hydroxides to balance out the 2 positive charges for my beryllium. So with the names of ionic compounds, the assumption is that you have the skills to figure out what the charge of each ion is, and from that, figure out what the chemical formula must be. This is very different from covalent compounds. With covalent compounds made out of nonmetals, oftentimes there will be a part of the name that tells you how many of something there is. So for example, carbon dioxide, the di in there says, hey, this is a carbon with 2 oxygens, right? That is oftentimes the case with covalent compounds. That's never the case with ionic compounds. With ionic compounds, they just assume you can figure out the charge of the ion, and from that you can figure out what the chemical formula must be. So if you're ever trying to solve like a chemical equation, you're like, well, I need to have more beryllium to make this work. You might be able to say something like, oh, well, I could have 2 molecules. I could change my coefficient, right? I could have more molecules of this. But I can't just change subscripts willy-nilly, because this is the set of subscripts that work. This is the set of subscripts to say, hey, there's 1 beryllium and there's 2 hydroxides that makes this a neutral compound. And that's just like a little bit tricky, but a thing to bear in mind about ionic compounds. A lot of these skills, like recognizing the charge of ions, is a thing we're starting to take for granted. All right, so the alkaline earth metals are alkaline. They can form weak bases. The last part of the name is alkaline earth metals. These things are found in the earth. A lot of gemstones are actually made from salts of different elements. And a pair of them come from the alkaline earth metals. So here we've got emeralds. Emeralds are made out of beryl salts, and beryl salts have beryllium as the cation. Yes?
Oh, so that's how they make like lab work.
Yeah! So this brings me to a really great point. Gemstones, they're just chemicals. A gemstone is simply a chemical. Yeah?
Is that how scientists make crystals?
Yeah, we can grow these in a lab. And the ones you grow in a lab are chemically identical to ones we pull out of the earth. In fact, if anything, they're probably purer, right? And more perfect than ones that are pulled out of the earth. Chet?
So we can just like make, why are emeralds like expensive then? We can just make them.
This is a fantastic question. Here's the reason why emeralds are expensive. There are corporations, right? A very famous example of this is the De Beers Corporation, which controls the release of diamonds. They effectively have a monopoly on diamonds. They like own all the diamond mines. They work together with all of the people who have access to diamond mines. They've set up what's called a cabal, right? And that cabal has put together a monopoly, and they've agreed, like, okay, we'll only sell X number of diamonds every year so that we can ensure that the price remains high. Now you might say, okay, but can't I just buy lab-grown diamonds? Wouldn't that ruin their whole entire monopoly? The entire goal of this cabal to extract more money than this thing is worth? And the answer is yes. You absolutely can simply buy a lab-grown diamond or a lab-grown emerald or a lab-grown ruby.
Are they cheap?
They're way cheaper. They're higher quality. And most importantly, I want you to take a moment and think about things like, where are these gemstones? Like, a lot of emeralds are coming from the southern half of the continent of Africa. A lot of emeralds come from places like the DRC, the Democratic Republic of Congo. 80% of the world's rubies come from Myanmar. And that is a country where the sale of those rubies is actively funding an ongoing genocide against the Rohingya people.
Wait.
This is true for a huge number of gems, and more generally speaking, a lot of minerals, actually. That a lot of these things that are mined, take a moment, imagine somebody who works in a lab, right? Have a picture of them in your mind, right? They are somebody who has, is able to pay their rent, right? Or pay their mortgage, who can afford 3 meals a day, right? Who's receiving a living wage and probably has health care, right? Think about the lifestyle of somebody who's working in a lab growing diamonds. And then think about the lifestyle of somebody who is working in a mine, right? Even in the United States, mine workers are not treated well, right? And when you think about other parts of the world, there are children your age who are working in mines in the Congo, right, in the DRC. And not only are they working in mines, which is incredibly dangerous, so high odds of them being harmed by this work, there are many enslaved people in those mines as well. Slavery continues to be a problem worldwide. And the funds from the sale of those gemstones are going to support groups of local militants who are actively engaged in conflicts that are harming those people's neighbors and families. So there's folks who are literally enslaved, and the profits of their labor are going to harm their families and their neighbors. And that's the case with a huge number of gemstones that come out of the ground. So why do people buy? Why would we give our money to De Beers? The only reason people give their money to De Beers is because there is this marketing lie that De Beers is constantly telling you. And that lie is a diamond is forever. It's this idea of a diamond as something sacred, something natural and holy and special and representative of love. And if you don't spend at least 2 months of your wages on a diamond engagement ring for your fiance, then you must not really love her.
Wait, what is a diamond made out of?
Carbon.
Oh, carbon.
Yeah.
So you can make your own diamonds?
We absolutely can make our own diamonds, and they are higher quality and they are cheaper than ones that come out of the earth. I think that you probably don't have the necessary equipment to do that. It requires a lot of pressure.
If I were to become a scientist and make emeralds and diamonds, can I just make a ton and just take them?
They're not that expensive, right? The thing about these things is they're just chemicals. The price of them is entirely propped up by an artificial view of value that is created entirely through monopolies, right? Basically, they're diamonds are not actually that rare, right? It's just that the De Beers Corporation will only allow a certain number to be sold each year.
So why would so what's the difference of buying diamonds and emeralds that are from the mines and buying them from the lab?
If you buy one from a mine, it's more expensive, and it's possible that your purchase has resulted in significant harm coming to somebody else. The value is entirely propped up by this marketing lie. So these are not actually things that are valuable. This is a huge amount of capitalism. And our society is based around the idea that hey, artificial scarcity props up a lot of these things, right? A lot of the lack of the world grows more than enough food to feed every human, right? But not everyone's actually getting fed. It's because there's a lot of work that goes into profits. right? Making sure that things are profitable. Same is true with these things, right? You simply have the power to refuse to buy gemstones that came out of the earth. And if you do that, not only are you saving money and getting a higher quality product, you're also ensuring that you are not actively funding evil across the world. It is, and the easiest thing you can do to not accidentally be causing harm. And there's simply no reason not to do it. It is only marketing that props up conflict gemstones.
So we should buy lab grown?
You should buy lab grown, or alternatively, secondhand.